All right, so now that we have solved the world's mysteries, so what do you do about bubbles in soda? They're supposed to be there, right?
That's okay.
So the other problem is if you're looking at soda and there's not bubbles there, then it doesn't taste right. That's a truth. Yeah, flat soda is not good. What's up? You okay with flat soda? Like preference, or just you'll so you'll drink flat soda before you'll drink water with bubbles in it?
Wow.
It's a pretty messed up guy.
Because I don't drink soda that much, so I like come off when I drink soda because it's carbonated.
Okay. Oh, so you prefer flat soda?
I don't know if I would say that. I enjoy it, but it hurts going down a little bit.
This has opened up a whole new, a whole new thing.
This whole thing hasn't been recorded.
It started. It's
Oh, you did?
yeah, just now. So the last couple of
Okay, so
minutes.
that's on there.
So we
Yeah.
didn't talk about the milk bag beer helmet.
Yeah, we didn't talk about the milk bag beer helmet on recording until right now. And it was a chocolate milk bag beer helmet. We should be unambiguous as programmers, right? It's the, all right. So homework assignment. What were we supposed to do?
Add before, add after.
Edit index.
Oh, added index. So what does this thing currently do? I don't have a running emulator? Oh, that makes sense because
I went into the Mac lab to get the emulator to properly work because I couldn't ever get it to work on my laptop, and we could not get Android to set up on the computer. It always said that it failed.
you mean Android Studio?
Yeah.
So you tried to install it.
To kind of like upload one of the phones, like the SDV or something like
Yeah.
that. And then every time we'd upload one, it would say that it would fail. So we couldn't get just even one of them to work. We spent like an hour trying to get just one phone to work. Just kept on saying that failed.
All right. So do you remember which machine you used down there?
Yeah,
Or you tried multiple machines?
I'll just try one machine.
Okay.
Try multiple machines.
Well, I mean, it might be worth trying at least one additional machine just to make sure it's not that machine. Was Android? I thought Android Studio was already on the machine.
Yeah, they are. Just not like it hasn't been opened up before.
Okay.
So.
Oh, so the problem was since it hadn't been opened up, like it hadn't gone through like updates and stuff. Okay. And you didn't. And did it? I assume it was asking you for like an administrator password. So that was the problem. Okay. So if you want, we can just pop down right after class real quick and go into that machine, and then I can get it updated. I'll just put in the administrator password. If you don't have time right after class, we can come in this afternoon
Okay.
as well. I should be around. Okay. Oh, so at the end of class last time, I was showing you how to get to another screen, right? So we're going to start working on stacks on another screen. And then, so last time we solved the homework assignment of learning where something is. Do we actually also do add and remove an index? Do we write that code, or was that something you had to write?
We did remove, but we had to write the edit.
Okay, so you had to write added index. We did remove an index, and then you need to add buttons for both of those. Is that the?
We have the menu. Like if you click.
Oh, if I click one of these guys, okay. Now I can say add above or add below. Got it. Okay, we're on the same page. All right. Okay, so let's go ahead and write remove an index for. Oh, we have remove an index. So if I click this, will this guy actually remove? If I delete it? Okay, got it. And it stays that way, I assume. So then, but if I click here and I say add above, that's not a working thing at this point. So we want to go ahead and grab this number and try to add it above this. So we already know where he lives. Now we have a function that will tell us where in our list the guy we clicked on lives, right? And we know how to add something, but now we're saying if I want to add it above him, I want to add it at the index right before him. So we need to go write added index. So we'll go into linked list. All right, so there's our remove. Oh, here we go. Here's our added index. So this guy's going to take in the value. It's going to take in the index, and it should add that guy to the proper place in our list. All right, so we can go ahead and ask if the index is equal to 0. We should probably just go ahead and call add front, right? So if index is equal to 0, let's call this dot add front, passing it the value. Else if index is equal to, what would it be, the last, is equal to what, the count, then that would be adding at the end. Okay, so we'll say this dot, if it's equal to, this dot count, we'll do this dot add end value. Otherwise, we need to go and I assume we had the exact same logic down here. Oh, here was our error we wrote for that guy. Suppose we could write an error for this. Otherwise, so if index is equal to this dot count minus 1, that's the last guy we want to remove. But adding at the end would be equal to the count. So if we want to remove the last element, it would be count minus 1. That's the guy we want to remove. If we're adding to the end of the list, we would say there's 5 things in the list. We're adding it at bucket 5, even though the last dude is 4. Because we added at 4, it would actually be before that, pushing the other guy down. So this should be right. All right, so otherwise, we need to go ahead and create a new node. So we'll say node n is equal to new node. And our node class right here takes in just the payload. So we'll go ahead and build that guy. So we're going to say value. So now we have our new node. We know where we're adding it. So if we draw our picture here, do I not have Keynote open? Okay, let's reassign some of these guys here. All right, so this is 0, 1, 2. So let's say we're adding it at position 2. So if we want to add a new node there, so we just built our new node, this is going to be the node 6. We'll steal this real quick. All right, so this is the new node we are adding. We just built him, so this is n right now. And we want to add it so that it's in this position. That is, that 17 points here and this guy points here. So what we need to do is we need to get ourselves into position where we have some of these counters. So we can get to our node before, our node at, and probably our node after as well. All right, so we want to set up these 3 pointers just like we did before. I think we could do it with less than 3 pointers, but 3 pointers actually makes it pretty easy to do it that way. So we're going to go ahead and we know that, or at least we're assuming, because we actually clicked on an index, we can assume that what we're trying to remove is a legal position. We're not doing error checking right now. So we know we should be able to go to here. We know that we definitely can go to the guy right before him, right? And then we know that that guy should be, might not be a thing, but he's certainly a value we can get by asking this guy about his next node. He might be the end, although we would have, in this case, he probably wouldn't be the end, but it doesn't matter how we're gonna, because of the way we're gonna get him. So we're gonna get node before, node to remove, node after. So let's do, this is node before. This is node at. And this is node after. And we're going to start node before off at self.head. Where am I? I mean, oh, this dot. Wrong language. If you haven't had Swift yet, it's self in there instead of this. Okay. So now we're going to just write a for loop. So for int I is equal to 0, I is less than index, I plus plus, and this should be actually index minus 1, right? To get us to node before. So now we should say node before is equal to node before dot get next node. And then we should be able to say node at is equal to node before dot get next node. And then we should be able to say node after is equal to node at dot get next node. So the theory is that should position all those guys. So now we should have a picture that looks like this. This guy's now called node at. And then this guy's called node after. Okay. Now, we need to go ahead and insert this guy. And what does that mean? It means we need to have this guy point to the same place that node at points to. So that should be step 1, right? So n dot set next node to node at dot get next. Actually, to just node after, right? So n points to node after now. So node after points here, n points here. All right. Now we can make node at point to n. So node at dot set next node. Point to n. Then we can make node before. Oh, actually, hold on. We did this wrong. If we're inserting this here, this guy is going to end up being over on this side. So we actually want. If we're adding an index, this guy's going to shift ahead. So we actually want n, his next node, to point to node at that guy. So n set next node to node at. Then we can set, so node at still going to point to node after. So we actually didn't even need to know about node after in this particular case. Then we're going to say node before dot set next node to n. That should give us that. Node before dot set next node to n. And in this particular case, we never actually had to use node after. So here's our new guy n. First thing we do is we make him point to the same place node at points to. Node at already pointed to what we were calling node after. This isn't a thing anymore. So we didn't update this at all. And then we just updated node before to point at our new guy rather than the old guy. All right, so that should be add at index. So now we go back to our node class here. Okay, so this was, if we said delete, do this stuff. We have a couple of options. What do we say here? Delete, add above, add below. Okay. So else if item.getTitle, here, let's just steal this. And it is add above. All right, then we are going to grab our current value from the top. So if we're in here, the idea is that I should have a 5. Well, I might have a 5 up here, and I've clicked add above. It should grab that 5. Now, who owns this 5? That guy's inside of main activity, right? So there's our new value edit text, this guy right here. So he's a local variable of main activity. I don't have access to him in the node. So I need to give myself access to him in the node. And how would we do that? If I have a bunch of nodes here, and I have main activity, and main activity knows about this little edit text, and I need this guy over here to know about him, what do I need to do? Where do I have to put this edit text? In that singleton. Now main activity still has access to him, but now these guys have access to him as well. All right, so that's the whole purpose of a singleton, is we now have access globally. So we'll go ahead and we'll steal this, go into list core. Let's see, we actually gave ourselves access to main activity. Main activity, well, it's a private variable. I could make that public, but let's just go down this path. So we're going to say, well, we'll make it public. Public static that. Okay, that's the new value edit text. So then in main activity here, I'll delete it from here, and then it should scream down here. So now this guy's now called, this is from list core. Copy that real quick. List core. Oh. List core. So exact same value we had before, he just lives in a different place now, which means that we now have access to him inside of our node class. So if we want to add above, first thing I need to do is I need to figure out where he lives, right? And didn't we write that in list core? Where did we write that? Or is it node? Oh, it's in linked list probably. Index of. So we can ask our linked list to give us the index of the node we want to remove. So int pos is equal to listcore.ll.index of ourselves. Oh, do we call it self? Myself? All right, so this is going to get the position of us. Les, do we have that stored somewhere up here? Do we have pos already stored? Nope. All right, so we'll go ahead and get the position of ourselves. Now, if we're adding above, we want to add a new node at the position pos -1. Actually, is that correct? No, at pos. That's what we just did here. When we looked at our example here, if this was 0, 1, 2, when we added the 6 at bucket 2, he's the new 2, the 8 pushed forward. So we would add it at pos if they chose before. Okay, we would say pos +1 if they chose after. Okay. Down a line. All right, so now we'll go ahead and say listcore.ll.add@index. And what are we adding at index? We are adding a value, and that value is listcore. What we call it, new value edit text dot get text dot toString, and we're adding that at position pause. All right, so that's what we're doing if they chose add above. And we could just put this in an else, but I like to be explicit. So else if they chose add below, we'll grab the same pause. We could also just grab this one time, maybe put all this in an else and then ask some if statements in there, but this isn't going to hurt anything. So this is the position of our self. And then we're going to add at that position plus 1 if we're adding it after. Make sense? All right, and in any of these cases, we'll go ahead and ask our linked list to redisplay itself. Again, we have some duplication of code here, but this at least keeps it compartmentalized. So write something that works first, and then if it makes sense to go back and streamline it. So generally speaking, I would say that if you were looking at this from a good programming practice perspective, the fact that we're defining this exact same value 2 separate times, and the fact that we're always telling our linked list to display, probably means we should move this line into a position where it always happens regardless, and that we should just do this line one time. That's the technical good programming practice approach. Now, having said that, since we're still learning this stuff, I think that this is a reasonable approach to it, where you're saying if we say delete, self-contained, this is everything we do when we delete. If we say add above, self-contained, this is everything we do when we add above. I think there's some value in keeping things self-contained for us right now at the cost of a couple of extra lines of code. Make sense? All right, but I do want to advertise that generally speaking, this would be considered not great programming practice, because one of the goals of object-oriented programming is to minimize duplication of code. And clearly in a 5-inch period here, we have some duplication of code. But it should be okay. So now if we choose add above or add below, it should put the stuff in the correct place, assuming we wrote add at index correctly, and we're doing our correct math on pause and pause plus 1. So let's see if that's the case. All right, so let's start by doing, here we'll put a 5. Let's try to add a 5 above the 7. Okay, so there's that. So now let's try to do a 9. Let's try to put that below the 5. Okay, so far so good. Let's try to put we'll put a 9 below the 8. All right, so that probably called add end, right? We'll try to put a 9 before the 6, add front. Let's try to put it after the 9. Let's try to put it before the 9. Okay, seems to be doing what it's supposed to be doing. Okay. And then we can certainly do our old remove front, remove end stuff. In fact, actually, as we have it set right now, we could probably dump all of these buttons, right? Because now, if we want to remove front, we just click the front and delete it. If I want to remove, did that delete it? That didn't delete it. Did we write delete? We wrote delete.
Wasn't the 5 hard coded?
It shouldn't make a difference.
The 5 wasn't hard. These are all numbers that we put in with that.
Well, it shouldn't make a difference anyways. I mean, the values that we added in are just like the ones that were originally hard-coded. We just added them to our linked list. That's interesting. So our...
Is it because we're not changing counts? remove it.
Oh, that probably has a whole lot to do with it.
It checks.
That has a lot, I think that has a lot to do with the problem. See, I was testing you. So go back to our linked list and our remove add index, or added index, this guy. When we actually add something, we need to say this dot count plus plus. That will be handled for us in the add front add end, right? Okay, but we were not incrementing it here.
I don't think we documented it in remove at index either.
Remove an index. Huh. This dot count minus minus. Okay, but just to clarify, make sure you're only decrementing and incrementing inside the else, because remove front and remove end handle it for us. We don't want to increment or decrement twice. Okay. So now this should behave better, I think. Okay, so let's, oh, I probably need to put a value up here first. We'll just put 9s all over the place. So we'll add above, we'll add below, we'll add below, we'll add above, all that stuff. Now I should be able to go in here and delete the 9, delete the 8, delete the 9, delete the 7, delete the 9, delete the 6, delete the 9, and we get our empty list. Okay, oh, but the funny thing is that if I do have the empty list, I have nothing to click on for our event, so we do still need the add front or add end, or we'd have to just make this guy clickable, which probably is overkill for what we're trying to do now. So we'll leave the buttons up there for now. All right, so that seems to be a pretty fully functional linked list. Okay, so let's go ahead and let's move to our stack. Oh, there it went. It just was slow. Yeah, so last time we were looking at that second screen and how it maintains its state. All right, so let's go back and look at that. Just before I forget, let me... So I need to commit first, right? Do I push? Oh, commit changes, that's what I want. So there's all my changes. So this is solution for homework 7, right? Then we'll do a commit and push. Okay, so that should be up there now for our solution for homework 7. All right, so now we want to go and start looking at our stack activity here. We're going to have a couple of things we're going to be working with here. So inside of our stack activity, and let's go ahead and close our linked list. We can close the r.java, close node for right now, close main activity for right now. Okay, so let's see, on this screen, in fact, actually, since we have multiple, so right now we have our count was 0. If we go back, then come back to this, it's not going to be. So the only way I can show you what I was trying to show you last time is for us to have a third screen. So if we go from this screen to another screen and then come back, you'll see that he hasn't changed his state. So certain activities can, well, we can control whether an activity is reborn or whether an activity is refreshed, like brought back from the background, and we use it again. So we might have an activity that has a bunch of stuff on it. So for instance, here, I think I could show it to you actually. If I am on this screen, let's go ahead and, this is the on resume function we wrote last time, but let's do it this way. So if I'm on activity stack, this screen, let's go ahead and give ourselves a button. Let's throw a button out here, and we're going to give that guy an on click. Button pressed. Okay. And then we'll come into our code for this, and we'll have public void button pressed view v, and we're going to go ahead and with that like that. Okay, so now we want to go ahead and we want to go back to our main activity. So we're going to create an intent. All right, and we'll go ahead and do that. And we're going to go to main activity.class. And we also have to give it a context, right? Is that this? All right, so we're going to go to that, and then we're going to say this dot start activity I. So when we click that button, the idea is it should go to our main activity. The question is, does it go back to our main activity, or does it go to a new main activity? Let's go ahead and launch this. Okay, so I'm going to put a 9 up here for right now. I'm going to click on stack, then we're going to click back. 9 is still there. All right, so now we're here. 9 should still be there. When we hit this new button, a brand new intent is created that goes to main activity class. So now we have a second version of our main activity. Well, what if we wanted to come back to the original main activity? So one of the things we can do is there's a thing dealing with activities that can say whether or not we want an activity to be reused. And it's going to be an Android manifest. We're probably not going to play with it now because we don't have a reason for it. It's one of these filters. Can we do it? I'll show you the function here real quick. Android activity reuse activity instance. Yeah, so that's launch mode single task. But it needs to be single task in order for us to do this. But let's try this. So I think that main activity actually by default is a single task. So let's try this and see if I'm lying to you. All right, so we have our intent to go to main activity, but now we're setting the flag to reorder to front. So if main activity already exists, what we're really saying is bring that guy back to the front, assuming he was created correctly to begin with, which I think that first activity is, and then we'll start that activity. So let's run this again. The hope is now we can launch main activity, but it actually goes, it just brings the original main activity back to the front. So we'll put a 9 in here, we'll go to our stack, we'll go to our new button, yeah, brought it back to the front. So that is not a new copy of main activity, it's now a the original main activity that was brought back to the front, which effectively means that we just made this button work the same as the back button. Make sense? Okay. May or may not be handy, but reasonable thing to consider with Android, how activities work. We talked a little bit last time about activity life cycles, where there's kind of multiple points in time where we can interact with the activity, whether it's about to come back, whether it's about to, we've looked at onCreate. That's the one we've been using all the time, which is when it's first born. But there are other times that we can look at an activity as well. So what we're going to experiment with here on this screen, since we're starting to move into this idea of a new data structure called a stack, which is a simplification of the data structure we've already been working with. So if we go here, so stack data structure, this is a linked list with 3 functions. Well, actually push pop, yeah, 3 functions. So we have peek, we have push, we have pop. So the peek function for a stack shows the top node in the stack without, well, let's say returns the top node without removing it. Push adds a new node to the front of the stack. Pop removes the node at the front of the stack. And really front, we would have used top instead of front. Removes the node at the top of the stack and returns it. All right, so a stack is known as a last in, first out queue. So think of this like a stack of magazines. When you have a stack of magazines, the very first, if you're putting a new magazine on top, you typically, well, if you're adding a new magazine to the stack of magazines, you typically would put that magazine on the very top of the stack, right? When you take a magazine off the stack, you remove from the top of the stack. So the last thing on was the first thing off. Make sense? Typically, we would not insert things in the middle of a stack unless we're going non-standard or something. All right, so that's what a stack is. So if we were to write our own stack data structure in terms of push, pop, peek, we already have a get at index, right? I believe we did. I've lost. Here it is. Link list. That's add at index, that's remove at index, that's index of, that's display. There's our get at index, except it's not written. Were we intending to write this at some point? Was that an assignment? We just never did it? Oh, so this is just, so I never assigned it, we never wrote it. All right, probably want to do this one real quick so we can implement peek. All right, so all this guy does is returns the node at a specific index, doesn't disconnect it, doesn't do anything, just here. In case you're interested, take a look at this node. And for right now, we'll just assume that the index exists. We'll ask the question. If I is less than 0 or I is greater than or equal to this dot count, we'll do system.err.println linked list index out of bounds, something like that, and then we will return null. Otherwise, we can assume the index is a legit index, so we're going to go ahead and move to the index. So we'll say node to return is equal to this dot head for int I is equal to 0, I is less than, let's call that pause, let's call this pause, let's call this pause so our i's don't conflict with each other. I is less than pause, I plus plus, And we'll just say node to return is equal to node to return dot get next node. And then ultimately we'll return node to return. Haven't removed it, haven't reconnected any pointers or anything. We just said, hey, give me the node at bucket 4. So we'll spin up to bucket 4 and say, here you go. All right, just a way of accessing an element of our linked list. So that's our get at index. So now let's go ahead and let's implement a stack. All right, so a stack is a linked list, but it's a specialty linked list that implements first come, first serve, or last in, first out. Go ahead, did I botch it?
No, I was just curious if with something like that, so if you're returning the node, like if you, wouldn't you still be able to modify that?
Yeah, you're giving them the actual node. So maybe your argument is, should we just return the value?
I was just, is that like what?
Yeah, it's a legitimate concern. So his question here is if I'm going to go through my list, I'm going to hand somebody the actual node. I'm actually giving them the ability to update pointers and stuff like that. So they can break my list if they wanted to. All right. So what we could do is instead of getting the node at a position, we could say, here's the value of the node at a position.
Or could you like create a new node with the
You could, yeah. So at that point in time, it's going to really depend on what you're ultimately looking for. Are you looking for the node? Are you looking for the value? Are you looking for a copy of the node? So it really has to depend on what you're applying it to. We're going to end up writing a game in here called Towers of Hanoi, which is going to be a stack-based game. And fairly simple game. We'll look at it actually here in a few minutes. But actually, we haven't written it before, right? We haven't talked about it? Okay. So we'll look at it here in a few minutes. But in that particular game, it would be beneficial for us to get the actual node because we're going to be moving it from one tower to another tower. But you bring up a good point. You know,
does the standard key function return back?
I don't know that there is necessarily a standard. I would say if you have a stack of nodes, peak would return the top of the stack, which is the top of the stack. So that would be a node. In practice, when you think about what peak means, you're peaking at the top of the stack. So you might just be interested in the value that's there, not the underlying structure. So you could probably make that argument validly on both sides, is I guess the punchline. So right now, let's just leave it at get it index returns our node. And now let's go ahead and create our stack. So we're going to create a new Java class. I'm going to call this guy a stack. All right, and we could say that a stack extends our linked list. So we can say he is one of those dudes. All right, so we'll go ahead and say public stack is equal to super. So that goes ahead and builds our underlying. Our linked list took in the ability to show himself, so it actually took in a linear layout. So we'll have this take in the linear layout just to match up to what we had before. So there's our stack, and then we'll just pass the layout to our parent and let our stack get built the exact same way that a linked list gets built. All right. So technically, a stack will have all of the functions that a linked list has, but we're going to only expose a couple of them. Okay, so what we're going to do here is if we make, well, let's leave that for now. We're going to say public node peak, and this guy is going to return this dot get at index 0. We're not doing any error checking, but That's what this will do. So it's going to return the top of the stack, not removing it. Public node pop will return this dot remove front. Public void push string value will be this dot add front value. So that's a stack. So once we have our generic linked list, implementing a stack is pretty easy, right? In fact, implementing a stack without a generic linked list is far easier than writing a generic linked list. So consider this as from a data structure perspective, and let me actually just show you a real example here. So we'll go to Towers of Hanoi. I think this is a real game. Yep, here we go. So the idea here is you have 3 separate towers, and each of these is a stack. And the goal is to get everything from this tower over to this tower in the same order. But there's rules. You can't put a larger disk on top of a smaller disk. So for instance, if I move this guy here, and then I try to do this move, that's not allowed. But I can do that move. That's allowed. And I can drag this guy here, and so on and so forth. This isn't going to be the most efficient solution, but whatever. So ultimately, you're trying to get the guys over to the other side. So I think it's, we're going to do this, then this, then this, then this, and this. All right, so that's our Towers of Hanoi game. Okay, so what we need to do is we need to be able to build a visualization of our stack. So our values are going to have well, right now we're storing strings, so because Java, if you remember back from last semester, we talked about Java as a string-based language. So if we can get something into a string format, we can pretty much do anything we want with it. So storing things as strings is going to be fine for us here. So the value that a disk, if you will hold, a node, is going to correspond to maybe how big this disk is. Okay, so maybe this disk has a width of 2, a width of 4, a width of 6, something like that, and then we'll draw it accordingly. Okay, so we want to go ahead and build this idea of a tower, something that looks like this, and we're going to add to that tower some disks. Okay, so we're going to start building that construct with a stack behind the scenes kind of governing it. Except our stack has a kind of a specialty purpose where we might need to peek at the top of a stack before we just haphazardly push something onto the stack to make sure that what we're about to push onto the stack is allowed to be pushed onto the stack. Make sense? So if I have this, I can't just push this guy onto the stack. I first need to peek at the top of that stack and find out, is it a legal move? Am I allowed to drop this guy on top of that guy? When I look at his value, I'll see, oh, his value is smaller than the value I'm trying to push. That's not allowed. Now we're applying the Towers of Hanoi rules to our stack. That make sense? So this is an example of using a data structure as the support structure for, we're going to say something real, an applied game. So this is going to be our Towers of Hanoi. And notice here that a pretty common thing is you can build up, your tower to be more complex and then solve it, and you can just do that. I'm very good at this. I'm drinking flat soda while I'm all right. Oh, stop. All right. 255 moves is the minimum amount of moves. Okay, so we want to think about this from our design perspective. So we're going to go into our layout, and we currently have we're going to do this in our stack activity initially. So we'll go back to here, and we're going to open up our XML. So let's burn this guy, and let's burn this guy, and let's get rid of our button and stuff. So here's our title, that stuff. We can get rid of that. Get rid of that. We no longer even have a button. We're just going to get rid of on resume. All right, so now we're back to a plain Jane dealie here. Okay, so we want to build a visual of our tower in here. All right, so what's a tower going to look like? So we look at these different things here. We have our linear layouts, which give us, so we can have a vertical linear layout. So we could add disks to that, and they'll plop down on top of each other, right? The guy will auto lay out disks for us. So if we start with that, that will allow us to kind of do what we're trying to do. Now on the background here, though, we might want to actually have something that looks like a tower. So what we can do is we can maybe put in a couple of let's see here. Maybe the best thing to do is going to be to set a background picture. All right, as opposed to, I can put an image view. We kind of want to layer this, where we want to have our tower kind of in the background and then be able to put stuff in front of the tower on the screen. How can we layer the stuff that way? It might actually be difficult without showing a different layout. So for right now, we'll throw our linear layout in here. So there's this guy, and this is going to represent our tower. We can always give this guy a background image, which will accomplish what we're trying to get it to accomplish. But for right now, let's just leave it like this. So here's our linear layout, and we want to be able to give this guy a, so let's give it a name. So this is going to be our tower. Okay, so anything we drop into this tower should get laid out vertically. All right, so now we want to have the idea of a disk. So we're going to go ahead and we're going to create another layout. Be a layout resource file, and this guy will be a is it disk like that or disk like that? That one? I'm not sure which it is. We're going with that one. All right. Throw him out there. It's also vertical. And for right now, we're going to go ahead and give this guy, let's maybe do it with, I guess for the sake of argument, let's do this with a button. So So actually I'm going to leave the button like that for right now. And we're going to set the gravity in here to center horizontally. So that should suck the button to the center here. And then we want to also drop it to the bottom. All right, so now we should build up from there. All right, and then we want this button probably not to have, well, we'll leave text on it for right now. So we're going to call this guy the disk. All right. And now what we need to do, we're eventually going to look at this through something called a fragment. In fact, we can probably do that now. So I'm going to go in to our project here. We're going to say new fragment, and we're going to make a blank fragment, and we're going to call this a disk fragment. Let's go ahead and let it create the layout. We'll just copy that thing over. So that's our fragment disk. So there's that guy. So I'm going to get rid of that disk XML. I will just open up the fragment disk, this guy. Okay, so that's currently put a text view in there. We're going to dump this text view, and we're going to go ahead and put a, oh, it currently has a frame layout. That should be okay. So let's do this. We'll just drop it there. We'll only use one frame. I think we could probably move that out of there, but we'll leave it for right now. All right, so this is going to be the tower. And then we'll go ahead and drop a button in there. And we'll set this guy's gravity to center horizontally and bottom, like we had before. Okay. And then we should be able to create instances of our fragment. So here's our disk fragment. That's only if we pass it some arguments. We're not passing in any arguments, but we should be able to create this guy anyways. So we want to drop, so let's do Android add fragment to activity. So we'll create an instance of our fragment and then add it to our activity into that layout. Okay, so here's our fragment class. This guy we just looked at had a whole bunch of extra crap in there. So we can add a fragment specifically using XML, but we probably want to do this programmatically. So here's our layout. So we want to create an instance of that fragment and then drop it into our activity. Is this the one that's going to show us the fragments in there? Yeah. Add a fragment to an activity at runtime. Okay, so here's our fragment. These are the setting arguments for our fragment, which we're not doing right now, but we can imagine, let's say you have sports scores or something like that you want to put up here. You can put in, current scores inside that fragment, and then it would add it to its view based on that information, and then when you add it to the activity, it would show up. So fragments allow you to kind of have, think of a fragment as being like an activity that lives inside of an activity. That's kind of what we want to have here, right? So that's setting the arguments, and then we're going to ask this activity to get its fragment manager, and we're going to add let's see, we're going to add to our fragment container, and in this case, our fragment container is our layout. So that should be okay. So the container that we have here, they've named it fragment container, but ours is called, did we call it tower? I think we called our vertical linear layout, we called it tower. And then we're going to be adding first fragment, which is this guy right here. Then we'll tell it to commit. So let's go ahead and try to add one of these guys to our code. So we'll forget about all this extra crap they put inside of our fragment here. We're not messing with the parameters anyways. Okay, good enough. So we'll go back into our stack activity, and we're going to go ahead and create our disk fragment. Frag1 is equal to new disk fragment. Okay. Then we're going to say, we're not setting any arguments, so we're going to get support fragment manager. So that's this dot get support fragment manager dot, call it just add on Pakistan. There's put fragment, but I don't think that's. All right, looks like we have to begin a transaction, then we add a fragment. This is to our container. Okay, and then the fragments of this guy. Well, let me pick that guy? Or is it just telling me what the parameters are? All right, so we want to give it our container view for this, which is going to be r.id.tower, right? And then the actual fragment is frag1. Okay, that should begin the transaction. And then is this a commit afterwards? Okay. So that should add that fragment onto our tower. Let's go ahead and hit play here, and the hope is that we get a screen that has one button all the way down at the bottom, and we know the button on the bottom thing is inside of our fragment, right? And then we're adding that to our tower itself, which is inside of our activity. So if this works, that'll prove that we were able to embed a fragment into an activity. Now, what's the advantage of doing that, of embedding a fragment inside of an activity rather than just adding a button to our activity and adding it as a subview or something like that? What do you think the advantage of that is? All right, so that broke, but what would the advantage of that be? Seems like when we look at fragments here, fragments have logic and stuff associated with them, right? They have all this stuff. In fact, I'm going to delete most of this stuff. Let's just look at their, I don't want this fancy fragment. I want a very simple fragment. I think all we have to have is the onCreate. Yep, onCreate view. We shouldn't even have to have a, it should give us an empty one. Yeah, I think this is probably where it was crashing. All these listeners and stuff like that. It was trying to get parameters that we weren't setting. All right, well, so the answer to my question is a fragment kind of has a mind of its own, right? A fragment is a full working program, just like our activities are a full working program. So fragments have multiple little things in it. They also have, onCreate, onCreate view. They have things that we can respond to within our activity, where a button is just a button. It's just something we see. It doesn't have a brain behind the scenes. So if we want to have aspects of our screen that have logic behind them as individuals, we would use a fragment to pull this off. All right, there's our fragment that's in there. Problem was it was all those extra buttons. So we should be able to see now, if I go back to our stack activity, I should be able to add. Actually, let's just steal this. And like this. So this should give us 4 fragments. Make sure this works, and then I'll give you your assignment. Push them off the screen, or they're laying on top of each other. All right, well, I guess for right now, for your homework, forget about the fragment stuff for your homework, but on the stack activity, make your stack activity work similarly to our linked list, our main screen that we have here, except you should just have push, pop, and peek. That makes sense? So when we hit peek, maybe it gives us a little pop-up window showing us the value at that position, something like that. So it's going to work pretty similar to this, except it's going to be a stack that you'll be showing here. So modify your linked list to show a stack. So I'll put this up as our starting point, and I will see everybody on, actually you can use the current thing that's up there as our starting point, and I will see everybody on Thursday.